In this lecture, we are going to discuss principal component analysis, which is a data dimensionality reduction technique. Firstly, we'll see the problem statement, that is dimensionality reduction. Then we'll discuss what's the need of a dimensionality reduction technique. Then we'll come to PCA, we'll discuss the mathematics behind it, and finally, we'll see the code for the PCA on iris dataset. The problem statement under data dimensionality reduction is to reduce higher dimension data to lower dimension data. We'll consider a data matrix X which belongs to real numbers n cross m, where n is the number of instances and m is the number of variables or the dimension of the data. We'll reduce this data to a data matrix X dash, where the number of instances remain the same but the dimensions reduced to m dash. In the above figure, the data is divided in 3 regions in a one-dimensional space. In the figure next to it, the data is divided in 2 dimensions, whereas the number of regions increase from 3 to 9. That is, from 1 dimension increase, the number of regions of classification increased from 3 to 9. So as the data dimension increase from 1, the regions squared. So with each addition of dimension, the number of regions exponentially increases. Now let us see how principal component analysis or PCA works. PCA is based on the assumption that the data has maximum information where the variance of one of its components is maximum. So the component which has the maximum variance will show the maximum information. So considering this component of the data, as a rough example, we can see the data has the maximum variance along this component, and it also contains, as you can roughly observe, the maximum information as the data is evenly spread along this component. To observe in detail, let us mark these axes as x1 and x2 and construct our data matrix X with 2 components x1 and x2 such that it becomes a real matrix of n cross 2 dimensions. We can now, firstly, as part of PCA, we'll center our data. This is important to reduce the computation and make the next process of finding the eigenvectors and eigenvalues easy. Once our data is transformed, so I've not drawn the axis here, so consider this as x2 and this as x1. So this is our transformed data onto the new x1 and x2 axis. So now our data is centered, so we find, let's call the transform matrix U such that the mean of U is 0. So we find the covariance matrix of U, which is basically a 2 by 2 matrix considering the variance and covariance between x1 and x2. So I'll just put it here, x1, x2 and x1, x2. So these entries represent the variance and these entries represent the covariance. So it's a symmetric matrix. So as you can see, it's a symmetric matrix. These diagonal elements will be different and these elements will be the same. So next we find the eigenvalues E1 and E2 of covariance matrix and their corresponding eigenvalues lambda 1 and lambda 2. The eigenvector here are the principal components of the data. That is, the eigenvectors will show the maximum variance along its component. So once we find the eigenvectors, we choose one of the eigenvectors and we transform our data along that direction. So this is our n cross 2 matrix and this is our 2 cross 1 component. So the new data becomes U dash, which is n cross 1, and we have reduced its dimension to 1, and we can see this observed process here. One another point we can note is that the eigenvalues represent the amount of variance the eigenvectors will hold. So the eigenvector E1 will hold a total variance of lambda 1 plus upon lambda 1 plus lambda 2. So this denotes the percentage or proportion of data information which the eigenvector E1 can hold. Next, we discuss the mathematics behind PCA. The proof of working of PCA is dependent on basically 2 factors, that is why the eigenvectors correspond to the principal component and why the eigenvector with the maximum eigenvalue is also the one with the maximum variance. So let us consider this figure with E as an arbitrary component where we have to find the variance along it. So the aim of this proof will be to find E such that the variance along E is maximum, and at the end of the proof we'll conclude that this E is also the eigenvector of the covariance matrix. So we find the variance as the sum over all instances and the dot product of each instances along E. So that is the projection of the data point on E. This term right here is the projection of data on E. So this length over here represents this dot product. As we have already centered the data, the same quantity can be represented as this. So we sum over all instances and sum over all dimension with j as the index, and we have xij and ej right here, and we square that. So next, we all also have one more assumption, that this arbitrary component has a unit length of 1. This is important, as if we don't consider this assumption, we can have any arbitrary value for the component of E, for the values of E, and the value will increase infinitely, and there's no meaning calculating the variance along an infinite component. So we take the norm of E to be 1, and we add a Lagrange multiplier right here to accommodate this factor. So we'll consider that along the j dimensions of this, it is equal to 1. Now, once we have our equation of variance ready, we differentiate it along this arbitrary component E. So E can be written as a vector E1 to all the way up to ED, where E1 to ED are the various dimensions of E. So along any one dimension, let's consider A, we differentiate it. After differentiating, we get this 1 by n summation I equal to 1 with n over here. This terms remain the same. The 2 comes out to be here. So dj equal to 1 along all dimensions, xij, ej, and the 8th dimension is differentiated, leaving this. The other component becomes minus 2 lambda e a. So now for considering the maxima, we put this as 0, giving us the equation that summation of I equals to 1 over all instances, 1 by n right here, and over all dimensions from j equal to 1 to d, xij, ej, xia is equal to lambda ea. What we do next is we shift the signs of these summations. So this comes out and this summation goes in. So the equation becomes, the dimension summation comes out, so this becomes d equal to j equal to 1 ej 1 by n. So as the jth index is not dependent on I, so this becomes I equal to 1, and over n instances xij into xia is equal to lambda ea. We can observe that while we differentiated this along any one dimension of E, this will hold for all a equal to 1, 2, all the way up to d. So I want you guys to look at this term right here. This term right here represents the covariance between, this term right here represents covariance for ath and the jth dimension. So when we write this into a matrix form, this becomes covariance. So let me put the summation here first. J equal to 1 to d ej. So all the dimensions of ej multiplied the covariance of a equal to 1 here with the jth dimension. And yeah, the jth dimension, yeah, that's it, I guess. All the way to here where it's still ej covariance for dth dimension. Also here a equal to d and here a equal to 1, and this becomes the covariance between these, and this is equal to lambda. This will be equal to lambda e1 and all the way to lambda ed, which can be finally converted into this will be our final covariance matrix, equal into e1 all the way up to ed and lambda e1 all the way up to ed. And now, as we can observe, this is the covariance matrix. We have the eigenvector here, which was firstly our arbitrary vector e. We have the eigenvalue here, and hence the direction along which the data shows maximum variance is the eigenvector, hence proved. Next, we're going to conclude that an eigenvector's variance is equal to its eigenvalue. We again take our equation of variance, summing over all instances and summing over all dimensions. We again ignore the mean term as we have already centered our data, but this time we split our summation terms, the square term right here. So this remains the same, I equal to 1 to n, and this we split between two indices. So this is j equal to 1 to d, xij to ej, and we take another index here. Suppose we take whatever, f, let's take f. So f equal to 1, x, I, f, e, f. Considering this, we move these summations out and this summation in. Let's make a color change. We get the equation summation of j, summation of f, and we got this 1 by n term here, summing over all instances, xi j into xi f, and we have here ef into ej. Now we got a pretty interesting term that we observed just right here. So this term is nothing else. First consider this term. This term is the covariance of j and f, and what we know, so covariance of this is j and f is x I j into x I f. So covariance of j and f multiplied, so this becomes v equal to summation over j, summation over f, covariance of j f multiplied by ef ej. This term right over here is equal to j from the previous proof. So this becomes lambda ej into ej, giving summation, the summation is of index d to d. So this summation becomes lambda eg square, lambda being constant, we move lambda out, summation eg square, and considering our equation that norm of e equal to 1, we get to be lambda. So variance, we prove that the variance of our eigenvector is lambda, its eigenvalue. Now we discuss the Python implementation of PCA. Firstly, we import the required libraries and import the dataset, iris dataset from the UCI libraries. The data frame columns are represented by the 4 attributes as given in the iris dataset, with the 5th column as its class. Firstly, we visualize the data, where the data frame.tail gives the 5 last instances of data. X is the data matrix as we have discussed in the previous portion of this video, and Y represents the class matrix, the class vector. We plot the data as a heat map on a 3-dimensional space. The first 3 attributes are represented along the 3 dimensions x, y, and z, whereas the 4th attribute is represented in color. So as we can see, the df.tail commands give the last 5 instances of the data, whereas the plot command shows the data on a 3D space with the 4th attribute represented as color. Then we center our data as discussed in the PCA technique. So we center our data by calculating the mean along each attribute, and we center our data. Then we find the correlation matrix, the covariance matrix of the data. After finding the covariance matrix, the eigenvectors and eigenvalues of the correlation matrix, the covariance matrix, is calculated. So as you can see, we have got 4 eigenvectors and their corresponding eigenvalues right here. We sort these eigenvalues according to their value, and next we show the percentage of data each of these eigenvalues eigenvectors contain. So the eigenvector, this eigenvector corresponds to this eigenvalue, which holds about 72% of the data. The second eigenvector, this eigenvector, holds 23% of the data. So combining both of them, we can get 95% of the data with dimensionality reduction of 2. So we consider the first 2 dimensions, and we create a projection matrix by considering these 2 eigenvectors, only the first 2 eigenvectors of all, and we dot product with our center data matrix, and we get capital Y, the reduced data set, and we can now plot it on a 2D plane as shown. Thank you.